really grateful for the invitation here. This is really highest level you can think of. It's one of the best universities in the world, and then very advanced studies here. Also, I'm a little embarrassed because most of you guys are sophisticated theorists, and I'm a very, very simple-minded experimentalist. So what you will hear is some thoughts about searches for new physics from a plumber's perspective, so to say. But let's get started. Before we get started, one more preliminary is I'm super happy that two of my students were able to come here and attend this lecture, so this series of lectures. So what are we going to talk about? So we have 4 lectures, or let's say sessions. I don't like the word lecture very much because it's best if you interrupt and we discuss. So in the first one, we will talk about low energy tests of fundamental physics, and I will first start with a little pep talk about tabletop physics and how it relates to accelerator-based physics. And then I will give you a specific example of parity violation in atoms with some personal perspective on this, on the history of the subject, and also on the latest work with Ytterbium atoms. Then in sessions 2 and 3, and by the way, this is tentative. I fully expect this to change. But the current plan is that in sessions 2 and 3, we will talk about ultralight bosonic dark matter. This is dark matter. C is smartly colored correspondingly with dark colors. And we will discuss nuclear magnetic resonance-based searches, atomic log-based searches, some specifics of looking for dark matter with sensor networks. If we could, dim the lights in front, this would be great. Actually, these monitors show you really how the color contrast should be, right? So,
you can go even dimmer, but then make it a little more difficult for people to take notes. You guys want? Should we go dimmer?
It's okay.
Okay.
Yeah. Okay. Anyway, and then in the last session, perhaps we'll discuss some new ideas for searches for interesting things such as gravimeter networks, searches for dark matter using antimatter both directly and indirectly. I see Pavel Fadeev smiling because that's his work, the indirect part. And then I will say a few words about something really fascinating. It's a sort of an alternative framework for what dark matter could be, and this is so-called axion quark nugget framework. We'll discuss that. And then we'll switch gears completely, and I'll say a few words about a new research tool that's currently being developed. It's basically how to take LHC and turn it into a fantastic light source that could be used for all kinds of things, including fundamental physics searches, perhaps. And parity violation in molecules, I think we already, well, we'll see how we proceed on this. So we'll start, as I said, with a motivational pep talk. And we'll start with discussing a topic of so-called law abiding natural world with a question mark. So, we have established a lot of knowledge and laws like quantum mechanics, general relativity, and so on. And this has reached, as you well know, enormous levels of sophistication. So you can calculate certain things like magnetic moments or something, anomalous magnetic moments to many digits within the standard model, and there's beautiful agreement. And you might think that things are doing well. So physics is doing well describing the world, but in fact, I would like to argue rather opposite. If you think back about the history of how quantum mechanics was discovered, or how special relativity was discovered, it was basically a very nice and solid body of classical physics, and then there was a few things we didn't really understand, few minor things, and then they blew into this completely different framework, quantum mechanics and relativity eventually. So it seems to me that now we are in the opposite situation. Despite of these successes that I just mentioned, actually one can argue that most of the things in the world we don't understand. We don't understand, most of the content of the universe. It's dark, dark matter or dark energy. We also don't understand really why the world is asymmetric with respect to matter and antimatter. And there are many, many things like this that are arguably not small but very big. So it's sort of very exciting, I suppose, if you want to put a positive spin of this. If small clouds in the past led to such great discoveries, then these big problems that I call elephants in the room, as you will see shortly, that they should lead to even more exciting discoveries. Anyway, we're trying to find some symmetries, and so when quantum mechanics was established, the concept of parity came up, and sort of became dominant. I don't need to explain to people in this audience what parity is, and people really used it a lot. One of the people who really liked symmetries was Lev Landau. And in fact, if you take Landau, I heard people discussing which textbooks are being used for undergraduate in the bus today. This is Sakurai or Griffith or something like this. Well, at the Novosibirsk University, where undergraduates were taught from Landau and Lifshitz, you know. So anyway, if you open Landau and Lifshitz, you see Landau never starts even thinking about the problem without first taking full advantage of all the symmetries that there are, and this really saves a lot of trouble. And Landau really believed in the P symmetry, and it was a big shock for him when parity violation was discovered in 1956, and he was really apparently in distress about this. But then he realized very quickly that maybe you can save sort of the situation if you say that spatial inversion is not the full symmetry, that you need to always, that the proper sort of symmetry operation, that you also need to flip the charges, and then the symmetry is restored. And he was so excited about it that he published, I think, this result in the Pravda newspaper somehow to be very quick. Now, I will tell you one story which I heard myself, and I don't know if it's apocryphic or if it's real, but I was told, and now I actually see this published. Some people publish it attributing this story to me, and this is really funny because anyway, the story was that Landau said, I believe so firmly in CP symmetry that I'm going to hang myself if it's ever discovered that CP is violated. Well, it was discovered that CP is violated in 1964. Now there are many tragic things associated with Landau. Tragic thing is that it was after his car accident, and so he couldn't follow up on his promise. Anyway, this is a picture of Landau. I think it was taken in 1938. And this is a mugshot. It's when he was arrested and put to jail for, you know what for? actually, most people in the 1930s in the Soviet Union, as in most communist regimes, are taken to jail without any reason because these are just terror regimes. But he was actually taken for a reason. He compared Stalin and Hitler somehow. Now, then there is a little bit of an interesting story about him. So he went to jail, and then Kapitsa, who was had a lot of clout, he was a Nobel laureate. He personally argued with Stalin to let him out, and he was let out after a few months in jail. But I happen to know a wonderful man by the name Yuri Rumer, who was a friend of Landau. And Rumer actually was in Göttingen in the 1920s and sometimes considered one of the fathers of quantum chemistry. So Rumer was immediately put to jail as the friend of Landau, the enemy of the people. And Landau was let out in a few months, but Rumer spent 25 years in jail and exile. Anyway, so that's a little, pep talk for you. Yeah. Yeah. Okay. So one thing I would like to say is that a lot of people are looking for physics beyond the standard model, and typically what happens is you write a standard model. Again, remember, Plummer is talking here. Okay, so you write the standard model Lagrangian, and then you say, oh, what if there is some other particle, relaxion or whatever, and you just write down some terms in the Lagrangian that correspond to this particle, and then you see what the consequences are, and you look for this particle. This is great, but this is actually sort of familiar grounds. But there is something that I call beyond the standard model, and that was mentioned actually this morning already. That there is also physics that I think is very important to look for and test. Just basically taking the lessons of the parity and CP violation that people believed them, but they turned out to be not such great symmetries. So we want to test CPT, for example. Or we also want to test quantum statistics or symmetrization postulate or something. But the problem is that these guys are in fact theorems within quantum field theory. So if you are searching for these things, you are searching for something that's beyond standard model, or I like to call it BBSM in that sense. Yes, and then actually it presents a little bit of trouble for experimentalists, because it's hard to work out experimental predictions. So, for instance, my group has looked for possible violation of permutation postulate for photons, and so basically you need to develop some alternative electrodynamics involving such violation, and that problem hasn't been solved. There are some theories that give you statistics violation in the non-relativistic limit that obviously doesn't apply to photons, so there's a problem. So this is a little bit of a strange area of science where I think it's super important to do these tests, but you really don't know what you are doing. So the way I decided about these things for myself is I'm going to do these things, but I'm not going to build my career doing only that because it's dangerous. Okay. All right. So I already mentioned in the very beginning that we have problems, big problems, and even bigger problems. I call these elephants in the room, and there's a list of questions. So I already mentioned matter-antimatter, symmetry, hierarchy. Problem has been mentioned before. There is also a peculiar strong CP problem, as you all know, that in QCD it's so easy to put violation of CP, and it doesn't seem to happen. So the parameter that drives that has to be you know, we think it's a phase, so it could be, say, depending on your convention, minus pi to pi or something, and it happens to be less than 10 to minus 10. Is that really a problem or not? But it's a strange, peculiar thing. And there are many other things, especially if you start talking about the dark side, dark matter and dark energy. For instance, there's another peculiar coincidence that, well, we say that there is 5 times more dark matter than normal matter. So on the logarithmic scale, okay, we have this roughly the same amount of dark matter and normal matter. Why is that? Why is it, you know, not 16 orders of magnitude more of one than the other? It's okay. So I will argue, as in fact all my lectures are about how you we're gonna try to solve these problems with sort of small scale experiments. And some people sort of like to say that, well, these experiments are replacing accelerators. I do not believe that. My personal sort of feeling is that there is actually a wonderful complementarity. You cannot do precision physics at z-pole on tabletop. Okay, you can do some physics even beyond the z-pole, but you cannot really do stuff that you can do with accelerators. And on the other hand, as you will see, these small-scale experiments, one of the beauty of them is that you know they can be done very quickly. You can you know, wake up with an idea to build a new LHC and tomorrow you have it. But I will show you some type of experiments that we have actually done that we thought are going to be a weekend experiment, turned out to be a month, but oh well, you know. So, okay. So if you are interested in this, I personally really dislike philosophy and general thoughts and so on. But I was kind of forced by my friends to write a little article about this kind of stuff, and if you're interested, it's in the references. All right, so where are we? There are very important questions to answer, and some of them are listed here, and all of these interesting questions can have some input from tabletop or at least small scale low energy experiments. And if you don't believe me saying this, you can read a review paper by a group of people listed here. Our chieftain was Mariana Safronova, an atomic theorist of unprecedented energy. I think this is our Mariana has so much energy that I think she's a solution to energy problems, you know. So, yeah. Anyway, so this is like a very, very thick paper. I think it has 100 pages or something, exceeding the limit of the journal by a factor of 2. Also, because Mariana is so convincing, I guess. Anyway, let us now move on to the topic that I want to cover in a certain amount of detail, and this is parity violation without T violation in Ytterbium. And as already mentioned, parity died, so to speak, in 1956. It is a beautiful story because it was actually T.D. Lee and C.N. Yang, shown here as very, very young people. I think one was a postdoc still, another was maybe beginning assistant professor. Very young people who said that well, there was a little problem in particle physics for seemingly two different particles having the same mass but very different lifetimes, and there was a little bit of a cloud, and they said that, well, this can be explained very nicely if there is parity violation. Now, you know, it's crazy. Why would we assume that? But But what they checked was that while parity was very well established in electromagnetic interactions, for example, weak interactions were never really tested. And they suggested experimental tests, and it turned out that the parity in weak interactions is violated, not as a small effect, but in beta decay, it's violated at the 100% level. And I found on the Wikipedia or somewhere Googling around this picture of Madame Wu and her famous experiment with cobalt nuclei, and this explains very, very nicely the physics of what is going on. So she had polarized cobalt 60 nuclei, and she looked at the direction of where the electrons were emitted from cobalt during beta decay. And she found that when the nuclei were polarized up, for example, the more electrons were coming down, and when she switched the polarity of polarization, so the cobalt nucleus spin was pointing down, then there was more electrons emitted up. So this is a correlation. We'll talk a lot about this type of correlation of sigma. This is the spin, in this case, of the nuclei, dot p, sigma p. So this is a pseudoscalar quantity, and this signifies violation of parity, because if this is a p odd quantity, p odd correlation that is forbidden by the law of parity. Yeah, so I really like this cartoon because it actually showed so p the spatial inversion, as you know, is when you take the coordinate axis and invert them through the origin, and actually sometimes people say that it's equivalent to a mirror operation, and it is. It's the spatial inversion is a mirror reflection and a rotation. Okay, so that's what it is. So here you have Madame Wu. It's sort of in the real world, and this is in the mirror world, and you see different things happening. So I really like this cartoon. But one thing I didn't like, I read a lot about history and about of this discovery and about her, and somehow I thought the physics is represented well, but it's not really her personality as I imagined her. So what did I do? I decided I go on Google and I look for a nice portrait of Madame Wu, and I found a really nice portrait of Madame Wu with I guess young people wouldn't recognize Gary Grant, but this is the older people will recognize a very famous actor. I was so very happy to find this picture that I was going around giving these talks, and most people would just accept what I was saying. But at MIT there was one colleague who said, "This is not C.S. Wu." I said, "Wow, I Googled it, come on." Well, the long story short, it turns out that there was a famous restaurant owner in New York by the name Madame Wu, and and Gary Grant was I guess, a customer. So I Googled some more and really found the real, yes, and I think it's, no, I think it's Goudsmith. Pauli, okay. Good. Anyway, yeah. So let's talk about parity violation in atoms. So in atoms, I tell you right away, this is not 100% effect. It's a much smaller effect. And one nice way to think about it is that electromagnetic interaction between the nucleus and the electrons, including the Coulomb interaction and magnetic moment interaction and whatnot, can be described by a Feynman diagram where you have a photon exchange here between the nucleus and the electron. and this is a long-range interaction. So the standard model, as we can use it now, tells us that there should be a diagram just like this with the gamma replaced by z. The difference that is important here is that gamma is very light and z is heavy. I think its mass is about equal to the mass of the chromium atom or something like this. And so so much so that this z exchange is actually a point-like interaction, not only on the scale of the atom, but also even on the scale of the nucleus itself. Okay, and so it means that in order for such an interaction to occur, the electron actually has to go inside the nucleus, and so this restricts the electronic configurations for atoms that can give you large atomic parity violation effect. But just like in the Wu experiment, the correlation is sigma dot p. So in this case, sigma would be not the nuclear spin, but the electron spin, and p is again the electron's spin. But this is a p odd even correlation. Sometimes these correlations are called rotational invariant. That's the terminology. In fact, a scalar or a pseudoscalar is a rotational invariant. Good terminology. Here's a brief history of atomic parity violation. So remember, parity violation was discovered in 1956, but neutral, but it was a beta decay. So this is in modern terminology charged weak current. So neutral weak currents were not discovered until the 70s. But in 1956, Yakov Borisovich Zildovich said that if there are neutral weak currents, then there should be an interesting effect that an atom in its ground state, in the absence of external fields, should act as a chiral molecule. Namely, if you have linearly polarized light, you shine into, say, a gas of such atoms, the polarization will rotate in some particular direction. It's pretty amazing. Okay, the next thing that he needed to do was to calculate the magnitude of the effect. And as any reasonable person would do, Zildovich decided to calculate it for hydrogen. And he did the calculation and came to a rather pessimistic conclusion that the rotation angle should be, I don't remember exactly, 10 to minus 16 radian or something per absorption length. And he said that he doesn't see any way to do this. But Zildovich had a very, very good habit. Whenever he had a crazy idea, he would write it down on 2 or 3 pages of exceptionally clear text, and he would send it to jet letters, and he would publish it. And you know, he had a number of crazy ideas apart from parity violation in atoms. For instance, one crazy idea was that if you have one particle and another particle and you collide them like this, then you have a very large energy release, colliding beams. That was one of his crazy ideas. Another crazy idea was of his was that if you have neutrons at very cold temperature, you know, then the de Broglie wavelengths will be larger, and at some point larger than the separation between atoms in a solid, and then the interaction of the neutron with the solid can be described with some sort of refractive index, like a photon interaction with a material. And then if you cool neutrons to some nanokelvin temperature or something, you can then put them in a bottle and carry them around in a bottle. Completely crazy idea. Well, ultra cold neutrons, you know what happened. I can actually continue this list. One day somebody should probably make a little catalog of Zildovich crazy ideas. That will be pretty impressive. Anyway, so this was a crazy idea until 1974. I think that was a year where actually weak neutral currents were discovered in neutrino scattering. And this sort of rekindled the interest in the topic. And then Marianne and Claude Boucher, I think I have a picture of the. Yeah, okay, no, not yet. I'll show you a picture of them later. Marianne Boucher is an experimentalist. She's now retired, and her husband Claude is a famous particle theorist. So they have this sort of family business of looking into this, and they discovered something very interesting, that actually there is an enhancement proportional to the cube of the atomic number of the parity violation effect. So the heaviest atoms have Z on the order of 100, so we are talking about a factor of 1,000,000 enhancement of the effect. And they suggested that in fact parity violations should be observable in heavy atoms. This is a very major discovery that got the field started, and this was sort of a start pistol for a few experimental groups to start looking for it. And the first people who reported non-zero results were Professor Barkov and Max Zolotaryov in Novosibirsk. I later on, when I had my first sort of lab work as an undergraduate student, I was very lucky to work with these guys. So they discovered exactly the effect that Zidovich predicted, this rotation of polarization in the absence of external fields. And several months later, Professor Eugene Comins and his students at Berkeley had observed another effect. In fact, the effect I'm going to describe to you in some detail. It's called Stark interference effect, and it was in thallium. And in between these two observations of atomic parity violation, there was observation of weak neutral current in deep inelastic scattering at SLAC. And so these things together sort of solidified the Weinberg-Salam model, and that became known as the standard model later on. So after this initial discovery, people sort of continued to work on this, and by the mid-1990s, this became sort of a field of precision measurement with sort of 1 to 2% measurements in the number of atoms and transitions. And then in 1997, a huge leap was made by the group of Carl Wieman in Boulder. They have reported a measurement in cesium atoms with 0.35% uncertainty. And not only there is a really precision measurement now, they also discovered something that's called the nuclear anapole moment, and I'll tell you a little bit later about what this is. But I wanted to tell you one thing here, that this is sort of a field where you have a professor and a couple of students working on it, so it's a very small scale effort, but it tends to take a long time. So I came to work with these guys as an undergraduate student around here, and my dream was to one day observe parity violations in my own experiment. Well, this came true 26 years later. At Berkeley, there was a lot of failures in the meantime, and finally at Berkeley we observed atomic parity violation in Ytterbium in 2009. Let me tell you, so I think this is important as sort of a general idea of how you measure weak effect using atomic systems. So if parity is conserved, then you can describe atomic states and assign a particular parity to them. So for instance, you can have S states with even parity and P states with odd parity. But because you have this weak interaction, none of these is an eigenstate anymore, and so there is a little bit of a mixture of P state to here and S state to there. And an interesting technical detail is that the mixing, the matrix element, has to be purely imaginary. And the reason for this, does anybody know why? No, good. Now you'll know. The reason for this is if you have a real part here, this corresponds to an atomic state, one of these or both of these states having a permanent electric dipole moment, just electric dipole of one state, and that contradicts also T time reversal invariance. And since we are studying now the effects that are P odd but T even, we have to avoid that, and this I avoids the T violation. Anyway, so the mixing coefficient is calculated by the normal perturbations theory. This is the matrix element of the weak interactions divided by the numerator, and so it turns out that the matrix element goes as Z cube. And in fact, there is also a prefactor here. This is called the relativistic factor, and in heavy atoms, it could be more than an order of magnitude. So I think it's a factor of 20 or even larger for francium atoms, and it's about a factor of 10, if I remember correctly, for thallium, for example. And then there is also the denominator here. This is the usual perturbation theory denominator, and it tells you, give you a little recipe. So you choose the states which have a large mixing here. So you have to choose the right configuration in a heavy atom, and you want to look for states where the interval between these states is kind of small. Yeah, so these are the I call them the parents of atomic parity violation, Marianne and Claude Bouchier. I took this picture when I had a great pleasure to work for I think some few weeks with Marianne, just guess when I was a postdoc through exchange. Right. Okay. So how do you measure this admixture? So one idea, the very first after the Bouchier law was discovered, right? The idea was, okay, let's do this. Let us have a system like this. Let's say this is an atomic ground state, and we have these nominally opposite parity states that are mixed by the weak interaction. And let's choose a system where this transition is completely forbidden. So not only by electric dipole rules, if these states are of the same nominal parity, this would be forbidden, but also say the magnetic dipole is forbidden. So really, really strongly forbidden transition. And then because we have an admixture of this state here, there will be a non-zero matrix element here. This will be an electric dipole matrix element. This one is allowed, and then we can measure this transition. That was the first idea that was actually pursued by the Bouchiers experimentally. But it turns out that the oscillator strength is so small, the transition probability. See, this is the transition probability that now will be the square of this weak interaction induced amplitude, and it corresponds to like 10 to minus 18 or something in the strength of the transition, that you can actually never really observe it because there are some background events, thermal excitation or whatnot, and you can never see it. So then what the Bouchier came up with a brilliant second trick here. They said, well, let us apply an electric field and introduce some stark mixing, some artificially induced mixing between these states. In addition, then in order to write the overall transition probability, how we would do it, we would say that the overall transition probability is, so this is atomic parity violation amplitude, and this is the Stark induced amplitude. Okay, and then we have to take the square here, and then we have, so we can neglect the square of this, as I just said, because it's a very small number. Then we have the square of the Stark amplitude is P conserving, and the interference term between the two. That is now linear in the weak interaction matrix element. So what have we achieved by doing this? We have achieved two things. First of all, we have made an amplifier of the useful effect. So we can actually now, we have control of how big it is. Changing the electric field, we can have this term being some reasonable, observable size. And the second is that we have introduced something that's called a reversal, and that turns out to be a concept that is central to all precision measurements, because you always have some kind of systematic, and the way you distinguish it is that you flip the experimental parameters and you make sure that the effect you are seeing satisfies the expected behavior, and this allows you to separate it from systematics. And this turned out to be, in fact, the most fruitful approach in this field. Some details. It turns out, if you work out all the matrix elements and so on, that in addition to the electric field, you also need to apply a magnetic field. And this is because if you take into account now the Zeeman sublevel of the system, the effect will average to 0 between different Zeeman sublevels, so you need to resolve them. And like I said, there are many controls of reversal and controls of systematic. And signal to noise nominally turns out to be independent of the electric field. And the way you see this, so your signal is proportional to electric field, as you see here. But the noise is, if it's a short noise, it's square root of your dominant signal. Then it will also be proportional to electric field. So the ratio is nominally does not depend, but like I said, you can't work with signals that are lower than your background. So Ytterbium. Ytterbium is a rare earth atom. It has Z equal to 70. Atomic number is 70, so it's heavy. Z cube is large. The ground configuration is this. It's a xenon atom with closed shells, and on top of that there is a field F shell here, and two 6s electrons. So it actually, despite of the fact that it's a rare earth atom, because most of the shell, all of the shells are filled in the sense, this is very similar in the spectrum to the alkaline earth atoms. Now, I mentioned in the very beginning that you need to choose electronic configurations that are proper. So the electron has to go inside the nucleus, for example. And if you look at the transitions in Ytterbium, it's not obvious that it's a good system for these experiments, and that's why it was actually missed by the pioneers of this. But in 95, David DeMille, now a professor at Yale, a very famous professor at Yale. He is, by the way, famous by the best measurements of electron electric dipole moment, if you know about that. He and I were students together, PhD students with Professor Eugene Cummins at Berkeley, and at that time David had a strange hobby. he would like stare for hours into tables of energy levels. I had a book of rare earth energy levels, and David would like read it for fun, and I didn't understand why he was doing it. But then he came up with a proposal. He said, actually, what the tables say is not really true. There are admixtures of configurations that are not listed in the table, and Ytterbium should be great for parity violation. And he published this in '95, and then, like I said, we have proven him right eventually in 2009. There's another thing about Ytterbium, that it has 7 stable isotopes, and in an atomic parity experiment, what you can do is you can compare the parity violation effect on different isotopes. I'm going to say more about this. And also, you notice that there are 2 isotopes, 173 and 171, with non-zero nuclear spin. And it turns out that these are non-zero nuclear spin is important to look for this thing that I already briefly mentioned called nuclear anapole moment. So this is doing weak interaction physics inside the nucleus using atoms, or hadronic weak interaction. All right, let me sip something because I'm losing my voice now, which is not good at the first lecture. So what do we do? This is now atomic energy levels, and the ones that were suggested by David that should be mixed are here. This the first excited even parity state where one of the s electrons is promoted to the d state over here, and then the closely lying opposite parity state there. So the small denominator, small energy distance between these levels provides one of the enhancement in addition to z cube. So this happens to be a strongly forbidden transition, and like I said, we are exciting it with a laser at 408 nanometers, and we also have the external fields applied for stark mixing and to resolve the Zeeman components. So after the atoms are excited to this state, they spontaneously decay into this triplet P manifold, and we can either observe this 556 nanometer light directly, or we can then take most of the atoms actually excite, decay into this metastable triplet P0 state. So we can take another laser and excite them to highly excited state over there, and then look for these fluorescent photons. And this way we have some enhancement. So for one absorption event at 408, we get on average about 3 photons that we detect in Ytterbium. And the way this looks in terms of the apparatus, to give you a sense, so it's a vacuum chamber. Obviously, it's about this big. You'll see a picture, a photograph, but maybe smaller, maybe like this currently. And inside of this vacuum chamber, we have, yes?
Can you go back a second to the second? What is the forbidden transition?
408. That's forbidden transition means that, so electric dipole is forbidden here by parity, right? And a magnetic dipole happens to be forbidden because of the configurations and terms here.
You say but don't you use a laser to excite from that level to that level?
Yeah. So this is the whole idea, is that you are exciting a forbidden transition, and it gets allowed by 2. It's forbidden, but this prohibition is so to say is violated by 2 things. One, the fact that this state has an admixture of that state due to weak interactions, parity mixing, and the other one is that we apply an electric field to additionally mix these states.
What I'm confused about is that you said this was time invariant, so wouldn't you be able to always emit, like you just absorb the 408 photon, can't you just emit it? I mean, just because of time invariance? I mean,
Yeah, but the probability to go here after you excite it is very, very small, because these are allowed transitions.
okay.
So once you excite that, then there is in principle a possibility to go back, but the branching ratio is negligible. All right, so here we have our Ytterbium oven, and we make basically a hole in this oven. We heat it to some few hundred degrees Celsius, and then we have basically atoms coming out. This is called an atomic beam. We collimate them with some kind of an aperture, and then they fly into the interaction region. And in this interaction region, the interaction happens between this 408 nanometer laser and the atoms over there. Now, the transition probability is very small, so we want to have a lot of photons that hit the atoms, and the way we do it is we do this inside what's called a power build-up cavity. So we enhance, we actually get the photons to bounce maybe several thousand times over here to enhance the transition probability. And this interaction happens in the presence of the electric field that we create with these electrodes, and we have coils for the magnetic field to separate the Zeeman components. So this is the first interaction region. So because we have all of this stuff here, the electrodes, the coils, and so on, we can get some photons out of there, but it's inefficient. So what we do is let me remind you. So most of the atoms that are excited here, they fall into metastable state here. That lives a very long time, and so these metastable atoms, they continue to fly along the vacuum chamber, and then there is a second interaction region where we have another laser. This one is near UV sort of, and this one is now red. And here, this interaction region doesn't need to have electric field plates or coils. So we surround it with a system of mirrors. So we basically collect almost 50% of all the photons and send them on a photodetector. And so this is the experimental arrangement, and our rotational invariant, and I invite you to check that this is also P odd and T even, as we want. No time reversal violation, but parity violation. And it's more complicated than in other experiments, but this is great. So you can see a lot of features of our effect. For instance, if we flip the electric field, our signals should flip sign, but if we flip the magnetic field, because the magnetic field comes twice here, it should not flip sign, but if we turn the magnetic field off, the effect should disappear. And then there's also this E is the linear polarization of the light, so we can also flip the polarization. So you can see all the reversals here in this invariant. So here are some signals. The signals, these are the three Zeeman components here. That's why you see three lines. This line shape took us a couple of years to understand in detail. It's a very interesting physics effect. In fact, we understand it. We can model it, but I'm not going to talk about it. And this was our 2009 results. So this is the parity violation amplitude in some units. Which I don't want to explain at the moment, but this is basically the parity violation effect. And this is no parity violation, and I believe so. So this is the mean value. So this was the range of theoretical predictions for the magnitude, and this was our result. So this was basically a confirmation of the very large on the scale of these effects can be large parity violation in Ytterbium, and in fact the parity violating amplitude is 100 times larger than in cesium. So this is so far the champion, that's the largest parity violation. In fact, it's observed in atoms. It's still tiny, but it's the largest.
Why did your error bar shrink as a function of around?
Because we were learning how to do things right. Yeah. So then I went to Mainz, and we took this apparatus from Berkeley to Mainz, and we rebuilt it. And I remember, so I said Ytterbium reincarnation. It reminds me that I went once to a conference in India, and there was a group. We had sort of a round table discussion at an actual round table, and there were people from different countries, and I mentioned the reincarnation of the Ytterbium experiment in Mainz, and I look at some of my Indian colleagues, and they, instead of looking at me, they're looking at the table. I said, what did I say wrong? And then one of them looked at me and said, here in India we take the concept of reincarnation very seriously. Yeah, so okay, sorry. Yeah, we do. So so we rebuilt this apparatus and improved it. And let me show you what happened. We did another measurement, and we did the measurement this time on different isotopes. At Berkeley, we just studied one isotope, 174, I believe it was. And here you see that the noise actually is different. The more abundant the isotope, the smaller the noise. And this is a sort of systematics and uncertainties table. And when you're doing an experiment like this, you're spending years filling out this table. But I never talk about this because it's the most boring thing to hear is how people study their systematics. So I'm going to skip it for you, but I'm going to tell you a little bit about the I hate the word philosophy, and then I use it a lot. But there is sort of a general principle how you control the systematics. So you saw the rotational invariant corresponding to the real effect. So what you do, you start by making a list of systematics that you can think of, and they are usually related to combinations of imperfections in your apparatus. Usually a product of three. A well-designed experiment, doesn't have these two imperfections. And then what you can do is you can artificially enhance, let's say, one or two of them, and then control the remaining one. And then when you reduce the other ones, then you know, sort of, you don't need to do the guesswork for your systematic. Then you can actually know what it is. And this I learned from my, as they say in Germany, Dr. Vater, my thesis advisor, Professor Eugene Comments, shown here at Berkeley with the EDM, thallium EDM apparatus. This is built. The funny thing is that most of the parts, most of the coils he wound himself, and most of the parts he machined himself for this apparatus. This is now sort of a different, much more hands-on style than most people, including myself, are doing these days. But that's how he did his experiments. Anyway, let me really not bore you with the systematics any further, but just to show, this is actually the same information that I showed you about the signal to noise for different isotopes, and here we have square root of abundance. So if you are short noise limited, this should be a linear dependence, and indeed it is. And now this boring looking plot is actually the money plot. This is the money plot. So what we have done here is we have done the first observation of isotopic variation of atomic parity violation. Now, in the standard model, you have a prediction that the parity violation effect is proportional to something that's called the weak charge of the nucleus, because basically all the nucleons, protons and neutrons, they contribute to the effect. And the weak charge of the neutron is -1 in the standard model, and the weak charge of the proton is 1 minus 4 sine square of Weinberg angle. Now, it so happens that sine square theta Weinberg is very close to 1/4 numerically. So, so basically, this turns this term off effectively, and the standard model predicts that the weak charge should be proportional to the number of the neutrons. And in fact, here is the number of the neutrons. So the isotopes we tested had this number changing from 100 to 106. And in fact, you can see this is a very nice confirmation of the prediction of the standard model. So now you might say, okay, who doubts standard model these days, and why is it useful? Well, I will argue that actually it's a search for physics beyond the standard model, not beyond, but just beyond. So okay, remember Plummer is talking. Okay, so the Plummer heard that the simplest extension for the standard model is that you should have extra z's, z primes, and in the earlier years, people said, well, okay, we will assume that the couplings of z prime are the same as z, but they're just heavier somewhere. And this experiment is not competitive for this extension of the standard model. But we can go back and say, aha, but what about very light z primes with very weak coupling, much smaller? Then this is sort of fair game. We can consider such an extent, but maybe you think it's not natural, but it's in principle this is possible. And we follow here the work of Victor Flambaum, and so we were actually able to constrain the coupling parameters for such bosons, and then we can combine with the cesium experiments. So the Ytterbium turns out is sensitive to protons. Combining with cesium, also you get the constraint for the nucleus, and you can see that it gets a cutoff at something like 10 to the 5 eV, and that has to do with the so that when the Compton wavelength becomes comparable to the size of the atom, you start losing the sensitivity. Yes?
Can it also be used to cast bounds on axion-like particles that couple DMUA?
I believe not for in general, yes, but not for these specific coupling. All right. So if you are interested in this, this is published. So this was the short paper in Nature and Nature Physics, and there is a longer paper mostly devoted to systematics in PRA, and if you're interested in details of that. Let's see. We have another half an hour, right? Is correct? Yeah, good. Okay, so the summary of parity violation in Ytterbium is that we measured the effect in a bunch of isotopes. We have about 0.5 accuracy per isotope. Remember, the most accurate world experiment by Carl Weyman has 0.35%. So we're per isotope. We are not there yet, but very close. And our next step is now going to these non-zero spin isotopes, and we want to. I will say a few words why we want to do this. So this work was done by a very nice team. So Konstantin Tsegutkin actually was the guy who was a postdoc at Berkeley, who was in charge of the Berkeley experiment. And Jason Stalnaker was a graduate student on that experiment. He's now a professor at Oberlin, and we invited him for a sabbatical summer where he came from Oberlin to Mainz and participated in these measurements. And Anne is a graduate student in the group who was also doing this the night shifts and so on. And Dionysis Antipas is the leader of this project. He does some other things as well, as you will see in later lectures. It's a very nice team of people to work with. So, atomic parity violation in the diagram form, if you want. So, what we've been talking about so far is, I already mentioned this. So you have the Z0 exchange between the electron and the nucleus. There is a second thing here, which is yeah. So okay. The important thing is that so this main process is independent of nuclear spin. So that's why we were talking about the nuclear charge. But there is also the nuclear spin dependent part. And so now there are three diagrams. So there is a standard model contribution, which is about 1% of the main contribution there. And this has to do that now the spin is carried by a valence nucleon, so you don't have this coherent enhancement as in the weak charge. So this is also described just by this diagram, except the axial and vector vortices are interchanged. The second reason is this parity violation within the nucleus. It has nothing to do with the interaction of electron and the nucleus. It's a parity violation within the nucleus. And it turns out that this is a comparable contribution. And another comparable contribution is, in fact, an interference effect between the hyperfine interaction and this diagram over there. So if you study the nuclear spin dependent parity violation, you can assess these contributions and hopefully say something about parity violation within the nucleus, in which there are still a lot of open questions, actually. Now, I mentioned this famous 1959 three-page jet letters by Zildovich, where he suggested the effect of parity violation in atoms. In the very same paper, on those 3 pages, he introduces the anapole moment. And where it comes from is the expression for the vector potential of the electrical current from the nucleus. So this is a general expression for the vector potential. And then you can start doing the expansion in powers of 1 over r. And if you take the zero term, it is 0 because the integral of the electrical current over the nucleus is 0. And then in the first order, you recover the magnetic moment interaction. And then in the second order, you find that this vector potential is given by delta of r, delta function, times this quantity a, which is the anapole moment. And this is basically r square j integrated over the volume of the nucleus. And this quantity is parity violating. And if you want to visualize what's going on, think of a long solenoid. A long solenoid with the current going around it in the winding has magnetic field inside and no field outside. Now take that solenoid and sort of wrap it into a toroid. And this toroid will also have the same configuration. There is magnetic field inside and no magnetic field outside. So that is the prediction of what parity violation within the nucleus would do. And so far, like I mentioned, this has only been observed in one case. And actually, this is a brief history now again of the anapole moment. So Zildovich proposes this in his paper in 1959. In that paper, there is a little footnote, I think, that says that Mr. Wax had a similar idea. There is no paper by Wax, so I don't know. But people didn't know how to measure it experimentally, and the recipe for measuring it experimentally was formulated in the 80s by Josef Hriplovich, yes, and his students then, Alex Ushkov and Victor Flambaum. And what they said is, well, all you need to do is to measure parity violation in an isotope with non-zero nuclear spin and compare the parity violation effect on different hyperfine components. And people started looking for it. The first measurement was done by Norval Fortson in Seattle, and they did not actually observe any effect in thallium. And Wyman and company discovered it in 1997, and there is actually still a certain amount of theoretical tension about why this is. So it depends a little bit on whom you talk to, whether it's a serious tension or not, but it's clear that it's interesting to do measurements in other systems, and that's what we're working on. All right, so that's all I want to say about parity violation in atoms. I have a few more things to tell you, but let's just pause here for a second and see if there are any questions, if any people are still awake. Yes, one person is awake. Yes, good.
If you could choose another atomic
System.
apart from ytterbium, what would you like ideally if you were to get it stable?
Yeah, so people, that's good. That's a very good question. Ytterbium is very, very good. So people try to do this isotopic comparison in cesium. Cesium has only one stable isotope, but you can make unstable isotopes, and there was a lot of effort to have a chain of unstable isotopes. Now there is still an existing effort in francium. Francium, so this is a heavier, next heavier alkali atom, and in principle it's as good as cesium with the effect further enhanced. But it's also it's a radioactive atom, and so you have to do it at accelerators, and that has been a big impediment so far. But maybe francium.
And it looks like you're going to go into molecules, but for just simple two atom molecular systems, do you use those at all to correctly?
Yeah, so molecules were suggested early on for parity violation studies, and nobody has ever seen molecular parity violation so far. So this is an open challenge, and in fact, that's what I'm going to talk about next. Pasha.
Was nuclear parity non-conservation measured in isotopes as well? Like you did for electron?
Yeah, I think so. Yeah.
They also did it for nuclear?
Yeah. Yes, I think so. Or like fluorine, I think, and some others. Yes.
There's just for the deprime coupling, like why can't it be extended to the case of axion-like coupling? Is it because of the vector-like coupling expected to introduce the boundaries, or is there like other reasons? So from where it is that a mediator can only be a vector mediator and not a superscalar.
Pasha, do you have an answer to this?
Or maybe because momentum suppressor. I'm trying to think of a reason.
No, I think it's for axioms that in principle the CD coefficient could be anything, but you don't have to specifically choose that kind of interaction. Like that
Then it
zero
should
down.
be like this. Can in principle be extended to like
Like you can write down the interaction C mu phi.
Right.
If But it's not like exactly the same thing that you were saying.
In principle, you can apply exactly the same, like you can apply the same logic from square one, but you can't just apply that final answer because it's simple dependent. It's model dependent the way that they've set it up, like the way that they've set it up the actual field.
But then one can reinterpret the data.
But you can, yeah, you can.
No, but the
It's just that it probably
usually
won't
you
be
can't.
as much of a
That's
constraint. It probably won't constrain it as much from
So there's a
Probably the cast bound is even like better than the one that
so
you.
that's a different statement, right? That this is not a strong enough bound.
No, but this is unrelated to the cast because cast uses photon interaction and this is an impermeable.
The derivative equation.
so this gentleman right here has made a catalog of exotic potentials due to different particles, due to scalars and vectors and so on. And we should look at that catalog and see which one is parity, which potential is is going to contribute here. And which, yeah. All right. So we can talk about chiral molecules. You know, a chiral molecule comes from the, where's Fotis? There. It comes from the Greek word kairos, right? A hand, correct? Yeah, with the hands, because there is a left hand and a right hand, and you cannot rotate your left hand into the right hand without breaking fingers, you know. So, and we don't want to do this. So that's why handedness and chirality is this word. So so you can have, as you can see here, a specific example of chiral molecules, and these are very different things. Now there is one interesting thing. So these molecules explicitly have an absence of mirror symmetry, and so they are not eigenstates of parity. Okay, so if you take a chiral molecule, say a left-hand molecule, and put it in free space forever, what you will find is that there is actually a quantum beat. Eventually, it will become a right-hand molecule, and after some time, it will become a left-hand molecule again, and then a right-hand molecule again. But we never observe it. And the reason we never observe it, so wouldn't it be nice, right? Sugar is chiral, right? So you pour your coffee, okay, and then you put some sugar in the coffee, and it's left-handed sugar, because actually all biological molecules have one particular chirality. And then you come back in half an hour, and it's all right-handed, which actually would be bad, because some molecules that are food, in the left-hand modification are poison in the right hand. So it's good that and the reason for why there is no oscillation from left to right was actually discovered, I believe, in the 1980s or maybe late 1970s. It's a very interesting reason why there is no oscillation like this. Professor Robert Harris, professor of chemistry at Berkeley, he discovered this, and the idea is it's sort of a little bit like quantum Zeno effect, if you want. So you have a molecule in solution, there are collisions, and the collisions constantly reproject it into one chirality. So it never, the quantum beat never has a chance to develop and really change the chirality. Okay, but the point is that yes. Yeah, of course.
Yes, but the different effects has to do, I mean, as much as you are looking on it, this is how much the probability that you will change the situation gets bigger, right? Gets smaller.
I don't.
I mean, as
Please
far as
explain.
you are looking at a molecule, let's say, in a specific situation, the probability that it will change its state is smaller.
Yeah, because of collisions, because the collisions they reproject. So if you
Okay.
yeah.
Sorry?
Yes.
It's confusing. how can our body be sensitive to chirality when we just agreed that only 90, 50, whatever you found the breaking of parity in the weak interaction?
This has nothing to chirality itself has nothing to do with breaking of parity. I don't think so. You just make a molecule out of many atoms, and you can make a left molecule and the right molecule, and it doesn't violate anything, right?
Sorry, only if there is.
Why would you expect the molecule to change its chirality?
Because if it's a free system, it's not an eigenstate of parity. It's so left-handed would be a coherent superposition of positive and negative parity, and then these are not eigenstates, and then it will beat. This is not related to weak interaction. Yeah, right. But what is related, I'll tell you, there's something interesting. A chiral state is not an eigenstate of parity. Now remember, I said that the mixing coefficient has to be P odd and T evens, and so we rejected the okay, how should I say this? Let me reformulate it a little bit differently. So for atoms, the diagonal element of the weak interaction is 0. It's only non-diagonal between opposite nominal states of opposite parity. But for chiral molecule, it's already the ground state is already a superposition of these two. So this weak matrix element has a matrix element of first order. So it doesn't have to be it can be diagonal. So there's a major difference between molecules and atoms, that here there is a first order shift. So in principle, you can measure it spectroscopically. And this was proposed also very early on, and people have been looking and improving sort of the sensitivity, but it has not been observed yet. We have an idea how to do this and some preliminary experiment, and let me share with you how to do this. So first of all, there is energy shift to first order. Now it means that if you're measuring any interval, spectroscopic interval between energy states in the molecule, this should be first order sensitive to weak interaction, and this includes, for example, the nuclear magnetic resonance lines. Now you can ask your theory friends to calculate what kind of effect this is, and they tell you that in the best case, in a favorable molecule with heavy atoms and so on, in the field of 20 Tesla, you should have about 1 millihertz line shifts. And now, if you have a mixture of left and right molecules, then no way you can measure it, because you have a line width of a resonance, and if you have two components and the shift between them is much smaller than the line width, you will never distinguish this. You will just see, you can see it's a small change in effective widths. Okay, then you can say, okay, well, fine, no problem. I'm going to do experiment with my left molecules. You know, pour them out of my NMR tube and put my right hand molecules and do the experiment again and see if I get the same result. Well, unfortunately, this effect is so small that you can never really control systematics. For instance, the drifts of the field in the time between experiments and so on. So this is hopeless. So what we are proposing is to use an effect that's called diastereomerism. And very briefly, this is the following. So you have your left and right molecules, and then you dissolve them in some kind of a solvent, and the solvent is also chiral. And what it does, a chiral solvent has a different energy shift depending on the chirality of your molecule. And this is actually an observable effect. And we have seen it in some, let me not bore you with the details of this, but what you see, this is the plot that is of interest. So here you see, this is basically your NMR spectrum, and here what we do in this direction is we change the chirality of the solvent. And if you have solvent of one particular chirality, you see very nice two lines corresponding to our two molecules that we put in an equal mixture, but we see them separately. Now we change, we actually add the chiral compound to the solvent, and we go through zero. When the chirality is zero, there is no splitting, and then we change the chirality, and now we see the splitting on the opposite side. So what is the parity violation effect? The parity violation effect would be that when there is no chirality of the solvent, we still have a little bit of a splitting. That's fine. In principle, we have sensitivity to see this, but the problem is, how do you know exactly where the chirality is zero? And here we have another idea. We take a molecule, and in a molecule we can look at different groups of atoms. And a theorist can calculate, good theorist, can calculate for us the sensitivity of different sites, of different groups of atoms to parity violation. And you can choose one group that is not sensitive to violation of parity, but sensitive to the chirality, versus another group that's sensitive to both. And then you here, what we use is hydrogen splitting, specifically that is only sensitive to chirality but not parity violation, versus carbon-13 splitting, and we got this very nice plot and our parity violation effect here. So remember, I said it's a millihertz at 20 Tesla. This is experiment at 20 Tesla, and here is 2 millihertz sensitivity. So basically, we have demonstrated that we have enough sensitivity to see this. The only catch is that the predicted effect in this particular molecule that's convenient for this experiment is several orders of magnitude smaller. So all we need to do is to take the right molecule and repeat this experiment. The right molecule doesn't seem to exist, and now we are talking to chemists who are trying to synthesize this molecule for us, but that's where we are. But it seems like it's very promising. Yes? Yeah, but as you can see, they're small. Yeah. Yeah. Yeah, of course we have error bars. Right. And so this is, in a sense, a built-in comagnetometer. So we feel that this is an interesting approach. Right. Currently, we are also working on another idea, and I'm afraid I sense that the audience is a little bit too tired, and this is not a simple one to explain. Let me just say that it's another thing, another trick in nuclear magnetic resonance, but it's a weird kind of magnetic resonance that happens at zero magnetic field, and there is another observable effect, and we're actually even more excited about this one than about the other one. I mentioned a good theorist that can calculate molecular parity violation for you, and here is the name of that theorist, is Mikhail Kozlov, our collaborator. And I think that's all I want to say to you in this first session. We have a couple of minutes for questions, if you like.
So when you're saying that earlier when someone was asking about probing parity and non-conservation in actual subatomic particle interactions, I see no reason as to why parity in molecular structures couldn't probe that if you had the right molecule.
Yeah.
Yeah. So then the barrier becomes what's the right molecule. Yeah.
And what's the right molecule, what's the right technique. So the experimental fact is that people have been really trying very hard, especially in the chiral molecule, because somebody made this weird observation. Okay, so life is chiral, and then people have done calculations of weak interactions in the chiral molecules, and there were some suggestions that weak interactions kind of favor the molecules that actually realized in life. I don't believe it for a second that weak interactions had anything to do with the choice of chirality. There are many more chiral effects, having to do with the polarization of the solar light and so on and so forth, that could have differentiated between chiralities. But nevertheless, this is often quoted as one of the reasons for the interest in these studies. Yeah. But we can also look, of course, for physics beyond the standard model once we start measuring it precisely.
You were being careful to talk about stuff that only violates parity but does not violate T. Are there also effects you can measure that are interesting that do violate CP?
Yes, of course. I will talk about some of them later on. And number one of these is the electric dipole moments of atoms and molecules. And it's a very powerful tool to study CP violation. Okay, well,